mail message yesterday, maybe it was the day before, I think it was yesterday, on that there is a Facebook group for this class where you might be able to get some useful information from each other. I monitor it fairly carefully. So join up if you want to. Are there any questions now about Lab 2 or Homework 2? No? Yes? Yeah, okay. Yes, so homework problem 1 or question 1 or whatever it is. I did a fairly lousy job on last time just saying, well, you just plot it up. What I didn't say was that you want to plot you want to use a sampled sine wave as input, but you're not necessarily analyzing it. You're not necessarily Fourier transforming it at the same rate at which you're synthesizing it. So you might be synthesizing at 8 kilohertz sample rate, but you might be analyzing it with your ears at 22 kilohertz bandwidth. And that matters as it transpires, as I'll show you in a minute. But so everybody's got a clear, crisp handle on direct digital synthesis. No questions. Wow. Okay. How many people got DDS working last night? 0. Okay. What did you do last night in lab? Keypad? You started with keypad. You got to start somewhere. That's okay. So in fact, there's no data about direct digital synthesis yet. Spectrum of a sampled sine wave. So, is the stick down here today? Oh no. Oh, there it is. So what I did let me just go to the next slide here. What I did was to write a MATLAB program that would output a certain number of sine wave valued steps per cycle with infinite amplitude resolution but finite time resolution. This is, and in your case, since you have 4096 amplitude steps, that's so fine, we're just going to call it infinite. It may as well be floating point. So the amplitudes are not quantized, but the times at which they are sampled are. And if you do that for two samples per sine wave, get a square wave, and this is a square wave that was generated with about 1,000 samples on it, but with only 2 samples per sine wave cycle. When you transform that, you get a square wave spectrum. This has unity frequency in Fourier transform space. So the first frequency component is the highest. The frequencies drop off as 1 over n, as it always does with a square wave. And why does it go up rather than down at 0 frequency? Because I didn't bother to offset it. So it's not symmetric around 0. It has a DC component. If we go to 8, so the first harmonic is how far down? What's the amplitude ratio between the fundamental and the third harmonic for a square wave? How many dBs down? Well, it goes off as 1 over n. The amplitude goes 1 over n, so it's a third the amplitude. And so what is the log base 10 of 3? I happen to know this because I memorized log tables when I was in college. Because, you laugh, because there weren't any calculators yet. So log of 3 is about 0.5. It's actually 0.47 something. So you'd expect you'd expect that the first harmonic, the first error harmonic, should be something like 10 power dBs down, 3 squared down. It's not good enough for this lab. If you have 8 samples per cycle, you can see more structure to the spectrum. And one way of thinking about this is that this sine wave is a linear superposition, is a linear sum of step functions. Remember what the Fourier transform of a step function is? Oh man. Yeah, well, it's right. So what you're seeing is a series of, so you have a set of step functions. You see a bunch of sinc functions here with a 1 Hertz modulation on them. That's why they're in pairs. There's the fundamental. This is in log units. So the ratio of the first error harmonic is about 0.25 over 0.3. It's about a factor of 10. You'll hear it. It's almost good enough, though, for the DTMF standard, which I believe is what, 20 dBs? 20 dBs. Factor of 10 is 20 dBs. Now, when you sum all of these error terms up, you'll probably actually get above minus 10 dBs, and so it won't be quite good enough. So we go to 16 per sample, 16 per steps per sine wave. Now the first error term is at the 16th harmonic. It is now a little over 1 log unit below the fundamental. And it's, of course, it's 16 times higher in frequency, which means you could build a filter that would pass this frequency and block these. If we go to 64 per samples per cycle, we have a ratio of something like 2 log units in amplitude. So I'm guessing, so really what I'm doing here is I'm working the first problem for you on the homework. You don't have to tell anybody that that's not in lecture. But what this is saying is that you're probably going to need between 16 and 32 samples per sine wave cycle at the highest frequency to make it go. Yes?
So did you use P-Welsh to generate those?
No, I just used the Fourier transform. P-Welsh would work too. But I was doing this really fast and cheesy. It was also, I hadn't looked at this code for over a year when somebody asked me the question in the last lecture, which was why my answer was so lame in the last lecture. Nope. You want it? What do you need? You just saw it. You want the code or something? Okay, I'll post it. Sure, yeah. It'll be in lab 2, right up probably by this afternoon, maybe by tomorrow morning.
So here, like your input, for example, in this one, it's like only like a vector of 16 points. So you just feed that to Fourier, you got this. Is that right?
You want to see the code?
Sure.
You'll be sorry. Okay, so I did the usual thing. I specified the time goes to 2 pi, so I get 1 cycle. I set a dt to 0.001, so I'd have lots of points. So it's actually 6,200 points in the FFT. Set the steps per cycle, number of points per cycle to 16. And then I do this weird thing that builds a step function. There might be a better way to do it in MATLAB, but you know, pretty soon you can't remember all the functions in MATLAB because there's 5,000 of them. But this just generates a stepped sine wave, and which is quantized in time but not in amplitude, and then plots the time variable and the absolute value, the log base 10 of the absolute value of the FFT. And it's truncated to the first 100 components because everything interesting was happening there. Straightforward. I'll put that up. Is that enough? Do you want more?
Yeah. So I saw. Yeah, I just wanted to see. So you have dt set to 0.001. Just do some small value.
I wanted enough resolution that it simulated a continuous Fourier transform. Again, any questions on Lab 2?
Still about the norm question in homework 2. We come up with an idea but you asked it should be minus 20 dB decimal, right? So we think it means that the error amplitude must be no more than 1/10 of the sine wave amplitude.
What it means.
Yeah, so we find the maximum error amplitude, which it should be no more than 1/10 of the maximum of the sine wave amplitude in amplitude direction. So it should. So if we divide the time direction into 10 pieces, so if we ask, so if
So what you're saying is you want to choose enough time pieces so that at any time the error in the amplitude is less than 10%. That is different than saying that the spectral purity is better than 10%. But that I could believe that's a reasonable thing. But is the slope of the sine wave is always less than 1, right? Because the first term of the Taylor expansion of the sine wave is what? Oh, baby. Let's think back to sine. Sine x is equal to x plus 1/3 minus 1/3 x cubed plus 1/3 x to the 1/5 x to the 5th, right? Isn't that right? So the leading term is x, so the slope is always less than 1. So you could be sure that if you take a delta t, that the error in the other direction will be the same. So a delta t of 10% will give you an x error of 10%. It's probably not good enough spectrally. It's close. Yeah, sine x is equal to x at small x. What else? What other questions on Lab 2 or Homework 2? Only 1 week left to get this done, folks. Yes.
Can you explain the amplitude modulation a little more with the different kinds given, so linear range, cosine, exponential?
Sure. So the question was talking about ramping the amplitude up. So you're going to have, the mechanics of it is that you're going to do the table lookup and you're going to get sine omega t out of the table lookup, right? You can't afford to do this sine operation, which is a floating operation, in real time, but you can afford to do the table lookup from the interrupt service routine. So you're going to do the table lookup to get this value. Then you're going to have to figure out some way to in your code, to mark a time zero. And from that time zero, which will be the beginning of the burst, you're going to have to generate another waveform, which you're then going to multiply times the sine function. This waveform can be as simple as a linear ramp up, a hold, a linear ramp down, where the 65 milliseconds, that's the minimum time required for the DTMF standard, is measured from 90% to 90%. It could be from 100% to 100%. You don't have to go crazy here. But it is certainly going to have to be at least 65 milliseconds from peak to peak here. So this is a relatively slowly changing waveform that you're going to be multiplying by a fairly quickly changing waveform. You could put this in another table. Could be in another table. It's easy enough to calculate on the fly. You could figure out a way of calculating that just by doing adds and shifts. If you want to make the spectral purity even better, you can get rid of all of the discontinuities in the first and second and third derivatives by making this a raised cosine. And then you will need to do a table lookup to get the cosine values at the beginning and end.
So the benefit of the cosine ramp is that there is fewer sharp changes. There's no technical derivative.
Yes, the advantage of the cosine, I mean, thinking of it in time domain, the advantage of the cosine is there's no discontinuous derivatives, so that suppresses the error terms in the spectrum. A square wave, a zeroth order discontinuity has a spectrum that goes as 1 over n. A break in slope has a spectrum which goes as 1 over n squared. A break in the second derivative has a slope that goes over as 1 over n cubed. The more of those terms you can suppress by getting rid of the discontinuities, the narrower the bandwidth. The difference between these two is pretty small. It's theoretically better. Is it worthwhile doing? I'll leave that to your ears. Before you choose a method, you could easily, in 5 minutes, do this in MATLAB and listen to it. And then say, is it good enough or not good enough? Then you do the hard part of putting it in C. If you have a problem with closed source, you can always use Octave, which is the open source version of MATLAB.
So we have to modulate two signals together. How would we multiply them with anything like heavier stuff?
Why not just use a multiply? The C, okay, without being a jerk. Let me say that the multiply in this architecture is rather fast. For two 16-bit values, it'll do this multiply in 2 cycles. For a 32 by 32 multiply, it has to do 4 of those. It's still pretty fast. So unlike some microcontrollers, a multiply is not a problem on this architecture. And that, for that matter, divide is in hardware also, which is fairly unusual. It's a 17-cycle divide. Does this answer what you were actually asking?
Yep.
Okay, so you'll have a slowly varying table and a quickly varying table that you're going to multiply together. You have to keep track of two different indices, changing at different rates. A lot of bookkeeping, but not so bad. What else on Lab 2?
Using about the product stressing, for example, if the timer calls the interrupt service routine, will it stop other thread?
No. The interrupt service routine will not stop at other threads because the interrupt service routine should exit in only a few microseconds. Yes, the other threads will be stopped. Let me clarify that. The other threads will be stopped while the interrupt service routine is actually executing, but it should not execute for very long. The key to sanity in any embedded programming endeavor is keep your interrupt service routines short, without state machines, no for loops. Nothing that locks you in the interrupt service routine. No, only the simplest conditionals. Keep it simple. No print statements in interrupt service routine, running at 100 kilohertz. Nothing time consuming. No TFT commands in interrupt service routine. Nothing that takes many microseconds to execute. Whatever you set it to. The sample rate of the DAC is set by how fast you load data to it. And so if you load a new data word every 100 kilohertz, every 10 microseconds, it'll be 100 kilohertz. You can use that at any rate you want. So I would say, again, I don't think you can sustain an interrupt service routine rate above a megahertz on this architecture. But with that limitation, you get to choose anything from 4 kilohertz up to make the sound you need. What else on Lab 2? So for Lab 3 now, you're gonna need a couple of new technologies, and one of them I thought I'd talk more generally about because you're probably, most of you haven't seen it before, and that's direct memory access. Have any of you ever actually seen a DMA architecture or dealt with it at all? Zero. Okay. So I'd like to talk a little more generally about direct memory access. And before I can do that, really need to talk about the memory architecture of this particular CPU. The memory architecture is linear, which is to say that there is a uniform address space that incorporates data RAM that you have access to. In this chip, it's about 16 kbytes. There's flash, which is where the program is stored, which on this chip is 128 kbytes. Since the memory architecture is uniform, you can actually execute code out of RAM if you want, because there is no logical difference from the CPU's point of view between flash and data RAM. So also in this are the config words. You know, when you do the pragma config stuff, there's config words which you generally don't want to mess with during execution unless you're the kind of person that patches a running Linux kernel on the fly. You mean you just shoot yourself right in the foot by doing that. But they're in the same memory space. And also the special function registers. All of the I/O registers that control all of the I/O ports, the timers, the direct memory access that we're going to talk about, all of the special function registers are in the same linear space. So they are uniformly addressed with a single type of number. They are uniformly addressed. And that's important because that means that you can get to anything with one access method, which is a read memory and a write memory. So the same low-level instructions which read data RAM are the same low-level instructions that read I/O ports. It's all the same. It's just memory access. The details of the memory bus, however, are kind of interesting in this architecture. It's not actually a bus. It's a switch. I mean, I've said bus a bunch of times, but it's really it's a crossbar switch. And there are bus initiators, which I prefer to call bus masters. And there are bus targets. There's targets. And the masters include the CPU instruction address, the CPU data address, the in-circuit debugger, which has higher priority than anything else, the DMA controller, which we are about to talk about, and then there's a thing called expansion. Who knows what that is? Any one of these devices can initiate a data bus transfer, can initiate a bus transfer from any place to any other place in this linear space. So for instance, the DMA controller can say, I want to read the analog to digital converter from a special function register and read it into RAM. And it can do that with no interaction from the CPU. Ooh, cool. So this gives you the ability to do some parallel computation, as long as part of the parallel computation is data motion. If all you need to do is copy data from a serial port to memory, memory to a serial port, ADC to memory, memory to memory, in other words, a mem copy, you can do that by setting up a DMA channel that will keep track of the source address, the source address, the destination address, and all of the transaction information necessary to do the transfer. Yes?
Well, you said you mean the internal one, right?
Internal analog digital converter, yes. So this is a separate processor that runs in parallel with the CPU. In fact, there's 4 of these. There's 4 DMA channels that all run in parallel with the CPU and do nothing, with one exception, do nothing but move data. The one exception is that there is a CRC, hardware CRC generator, cyclic redundancy check generator, that can be looped into any DMA channel and run at bus rate. So you can do a very fast error correction code, or error detecting code at least, using the direct memory access. It uses a linear feedback shift register in hardware, again, separate from the CPU. It does use a linear feedback shift register, 16-bit, which can generate a CRC, but also, linear feedback shift register. It also generates random numbers if you set it up right. Very fast random number generator in this case. Something like 3 million or 5 million a second. So the targets for this can be flash, RAM, or peripheral. And fact is, instructions can be retrieved from flash or RAM, but you're not allowed to retrieve opcodes from the peripheral, and that kind of makes sense. Otherwise, you'd be executing code from an I/O port. And every other entry here is a yes. You can read and write. You can read from CPU data from flash, from RAM. You can read the in-circuit debugger from any place. You can DMA to flash, RAM, or peripheral. Both read and write. It is very cool, because a lot of what you do in a program, particularly a data acquisition program, is move data around. And this just does it for you and saves you the whole CPU. As an example of the efficiency, one of the labs I used to use on the AVR, on the Atmel AVR, generated a television signal which requires about 5 megabits per second out of an SPI port on the Atmel chip, and generating that 5 megabits per second used about 80% of the CPU. On this architecture, it uses 7%. And the only reason it uses any at all is that there is an interrupt state machine that has to run to tell you where in the video frame you are. So the emphasis here is that this is separate hardware. It has a bazillion control registers, because you're going to want to set up a source address, a source increment, a destination address, a destination increment, a destination loop size, a source loop size, because if you're reading from the ADC, the analog to digital converter, into RAM, you're going to be reading you're going to write a whole block of RAM here, but you're going to be reading one value here over and over again. You're going to be reading the same ADC address 1,000 times, if you want to take 1,000 points, and putting it in a different 1,000 positions in RAM. So there's loop control. There's stop control. You can stop a DMA burst by any interrupt source, or by a software abort command. You can start a DMA burst from any interrupt flag. But here's the weird thing. You don't have to take the interrupt in an interrupt service routine. The DMA hardware will detect the hardware interrupt flag and do the whole start transaction operation in hardware with no interrupt service routine. That's cool. That's zero overhead. There's a pile of registers. There's good support for this in the peripheral interface library. The macros more or less make sense by name. But there's a lot of them. And I'll show you some examples that use this in a few minutes or maybe next time. Yes?
Can you use hardware triggers like comparators to start?
Any hardware that can generate an interrupt event, which includes comparators, will start a DMA burst.
But it's actually the interrupt flag, not the hardware itself.
It is the interrupt flag set by the hardware. Yes. You can also end a DMA transaction on a pattern match, so that if one of the bytes that it's reading out of memory happens to have a certain value, it stops. So you could use, for instance, if you were transmitting a string that you didn't know the length of, then you could stop on the 0 that terminates every string in C. So this is, to me, is specifically set up for stopping string transfers. You start the string transfer, you go do whatever you want, it stops when it's done. You can set up the DMA to be blocking or non-blocking. You can set it up so you start the transaction, the CPU goes on doing whatever it's going to do, and the DMA finishes when it's finished. Or you can set it up that the DMA hangs the CPU until it is done with the transfer. So, for the computer scientists here, we can do that. We can read memory. We can copy memory. We can stop on a pattern. We can do some arithmetic. We can do a CRC, which probably results in other kinds of arithmetic. Is it a Turing machine? I emailed Microchip to ask them this, and they wrote back, "What's a Turing machine?" So I probably got the wrong guy. But maybe it is. If it were a Turing machine, wow, then you have 5 processors on this chip. You think it is? I think it'd be worthwhile trying to prove it.
Can make branch decisions.
Yes, it can make branch decisions. Oh, because based upon the value, it can also decide to chain DMA. So it probably is. But that'd be fun to show sort of formally. Or for a final project, write a compiler that uses the DMA channel as a processor. So the 4 DMA channels are actually multiplexed. There's only one DMA controller. And so you have to choose one of the 4 DMA channels. If you ask to do 2 or more DMA transfers, then there's an arbitrator. There's a bus arbitrator that will cycle among them in some reasonable order. You can control that if you want. You can set a priority of DMA channels. But if you do nothing, they will send 4 bytes each in round robin. They'll send 1 int each in round robin. But you can mess with that. So this is actually a 4-way multiplexed channel off the 4 DMA controllers. You can set up the transfer to be 8, 16, or 32 bits. per transaction or more. The minimum data size that is transferred is a byte with no particular alignment. As I said, it could be manual start or interrupt flag start on any interrupt, any hardware event. It can be one shot or auto repeat. So you can set it up so once you start it, it goes forever, cycling through memory. Oh, what would you use that for? Well, let's say that you were targeting RAM on one side, a big block of RAM, which happened to be, say, a sine wave table. And the other end, you were targeting port B, to which you've hooked this parallel DAC. Then you'll produce a sine wave forever with no CPU involvement. It'll just sit there and produce a sine wave forever if you put it in repeat mode. So you have one shot in repeat mode. As I said, you can auto increment source destination addresses. You can generate interrupt events for done or abort, for source empty or source half empty, or for destination full or destination half full. So you can get early warning of when you're filling up the buffer due to a DMA burst. So that would be a case where the DMA channel would interrupt the processor and say, you got to do something, we're running out of memory here. There's also an interrupt for bad address. If you go off and do something crazy by asking to transfer data from a source that doesn't exist, then it'll throw a bad address interrupt. As far as I can tell, the CPU supports kernel mode and user mode. And when you bring the power up at reset time, it comes up in kernel mode, which means you have access without permission problems to every physical address. You have permission to shoot your foot off, in other words. So you have to be a little careful where you write stuff in memory. But you can write wherever you want. Any questions on this? This is a very powerful subsystem.
How fast is clock speed and also the interrupt the CPU activity?
Both good questions. One of the very first things I did as an experiment on this chip, once I could toggle the LED, was to set up a DMA channel, run it at full speed, just as fast as I could, and simultaneously toggle a port pin from main and ask, what did it look like? And I'll show you the answer to that next time, but I'll show you the waveforms, but the short answer is you could put out about 3.2 megabytes per second across one DMA channel and run the CPU at full speed with no interaction. It does scale because the 4 DMA channels are actually multiplexed onto there. And so what will happen is that you have a net throughput of only about 3.2 megabytes per second across there, corresponding to a bus transfer time of something like 100 nanoseconds per byte or something of the sort, or 150 nanoseconds per byte. It's pretty good. So let me emphasize again, you set up the DMA using the CPU, obviously. There's a whole bunch of registers you have to set up. Then you arm the system. You say send data on an event, or just start. You arm the system, and then you go away and it does whatever it wants to do. So it is completely independent of the CPU. I don't believe I've ever played with an architecture before, except for System 360, which was, big iron that had DMA channels, and it's pretty handy. You can make the TRT. Sorry, the proto-threads. The proto-threads. Default library that I wrote includes a function that does all serial I/O by direct memory access, which turns out saves, if you do a per character transmission, it saves most of the time, because each character at 9600 baud takes a millisecond. That's like 30,000 instructions. So you can start a single character and then go back and have another thread execute. But with the DMA burst, you set up the transaction, and then you don't have to look at any flags again until the whole string is sent. So it saves quite a lot of thread overhead by doing it in hardware. Questions? Another good question. Yes, if two modules, if two bus masters try and access the same target, there is contention, and you get to choose there is a default order for who gets first priority. The CPU, the in-circuit debugger, gets highest priority, then the CPU data, then CPU instruction, then DMA. But you can change that order. The examples I've been messing with have mostly been DMA between RAM and peripheral, with the CPU instruction coming out of flash, so that there wasn't a lot of contention. So this is the kind of thing, whenever you have these new hardware modules, these new things that run in parallel with the CPU, like SPI channel has its own state machine that barfs out bits independent of the CPU. The UART has its own state machine. The ADC is a separate subsystem that runs in parallel with the processor. DMA is a big, heavy processor that runs in parallel with the main CPU. Then you have to lay awake nights thinking, how could I possibly use this? What weird thing could I do with it that extends the abilities of the CPU? Keeps me awake at night. Any last minute questions on Lab 2? I will be in lab all afternoon. Let me remind you, on Tuesdays, I can be in lab Tuesday morning, but not Tuesday afternoon, because Tuesday afternoon is 2300, ECE 2300. Two groups showed up yesterday at 1 p.m. saying, when can we get into lab? The answer is, you can't. Today I will be in lab all afternoon. I will try and be in lab every Wednesday afternoon. If nobody shows up for an hour or so, I'll probably go back to my office. I'm going there at 1:30. That says 12, but in another month it'll be correct again. But so I'll be there probably in 20 minutes or so, and stay the afternoon unless absolutely nobody shows up. Thanks.